In this example problem, we are on vacation, and your 1,300 kilogram car pulls a 540 kilogram trailer away from a stoplight with an acceleration of 1.90 meters per second squared. Now, since the trailer and the car are moving as one system, we know that the acceleration of the trailer and the car is going to be 1.90 meters per second squared. So the goal of this problem, or part A of this problem, is what is the net force? So we want to find the net force exerted by the car on the trailer. So let's start by following our step-by-step procedure. Let's draw all of our forces on this picture. So we'll start with the obvious, which we know that there's a weight, so a force of gravity acting down on both of these. So we have the weight of the car. We have the normal force that's opposing that one. I'll try my best to draw these about the same size. So the normal force on the car. We also know there's the weight of the trailer acting down. Okay, so that's the force of gravity acting on the trailer. And then we know there's a normal force holding the trailer up. Now, obviously, these vectors are not drawn to scale. Then there's the normal force acting on the trailer as well. Okay, so as far as I can tell, those are all the forces acting on this system in the y direction. So now let's work with the x direction. So let's look at the trailer first. We know that in this problem there is a force, okay, being applied in the x direction. So there's a hitch here that is connected to the car and the trailer. So this car is pulling that trailer. So we know there's a force that's pulling this trailer to the right. So there's a force there, and we'll call this force sub C. So the force of the car on the trailer. So there's the force of the car pulling on the trailer. Now remember, according to Newton's third law, every action has an opposite and equal reaction. So if there's a force pulling on the trailer, we know that the trailer has to be pulling back on the car. So there's a force being applied to the car from the trailer. We'll call this force. So a little hat. Looks awful. Let's fix that up. So there's a force here. Force. And we'll call that sub T, so the force of the trailer on the car. Now, even though it may not be immediately obvious, there has to be some sort of forward force, so some sort of force pushing this car along. Now, I don't want to get into the specifics about how it's actually friction that's propelling the car forward, so I'm just going to, in general, write a force that is pushing the car forward. And we'll call this F sub P, so the force pushing this car down the road. So those are all the forces that I can tell that are acting on this system, or the ones that we really need to deal with in this case. So let's now go to the next step of drawing our free body diagrams and replace the object of interest with a point particle. Now in this case, what is the net force exerted by the car on the trailer? So we're curious about the trailer. So let's only finish drawing our free body diagram for the trailer. So I'm going to draw a point here at the bottom that represents our trailer that has the same mass as the real trailer that I have above. So the mass sub T is equal to 540 kilograms. 540 kilograms. We know that this trailer is accelerating, okay, in the x direction at 1.90 meters per second squared. Now, how in the heck did I know that my acceleration was in the x direction for this case? Well, let's just go ahead and make a pretty fair assumption that this car is moving parallel to the road. So if it's moving straight down the road, it's a pretty good assumption that this acceleration is only in the x direction. Now let's draw our forces on there. Okay, we have the normal force acting on the trailer. So that's acting up. So N sub T. And then we also have the force from gravity, so the weight of the trailer, and then we also have the force of the car acting on the trailer. So we'll go to the right, so force of the car acting on the trailer. Okay, so that's our free body diagram for the trailer, but not the car. We'll deal with the car separately if we need to. We may not even need to worry about that scenario. So since we're only concerned about the net force exerted by the car, then we really only need to work with the x direction. So when you use your sum of forces equation, so sum of forces, we're going to use the x version of our sum of forces, so MAX. Alright, so applying Newton's second law to this problem, and actually before I do that, I don't want to get ahead of myself. To make sure that I'm systematic with how I'm solving these problems, I am going to explicitly define a coordinate system. Even though right now we haven't seen any variations in the coordinate system, we will change up our coordinate system in the future. So in this case, just to clarify, I'm saying up is the positive y and right is the positive x. So up is positive y and to the right is positive x. So in this case, the f sub c, okay, the f sub c is only acting in the x direction, so it's parallel to my x-axis. So I know that the magnitude of the force of the car is going to be equal to the x component of that force. So maybe let's just go ahead and write this out on the next slide just so we have enough room to write out all the math. So we know that the magnitude of the force from the car is going to be equal to the force of the car in the x direction. So force of the car in the x direction, which we do not know. Okay, and the reason that we know that, again, is because the force from the car is parallel to the x-axis. So that means that the y component, so the y component, force of car, okay, the y component is equal to 0 in this case. Alright, now summing up all of my forces in the x direction, setting that equal to mass times a sub x. Okay, so let's look at the left-hand side, summing all the forces up in the x direction. In this case, we only have the 1, so we'll say that is F, so the force of the car in the x direction. Okay, now since that is the only one, I just say that's equal to. Now, what mass am I using here? This mass is the mass of the object that we are looking at, which in this case is going to be the trailer. Okay, so we're looking at just the trailer for just a moment, so we're only going to use this m sub t. So the mass sub t, and then of course the acceleration of the trailer in the x direction. Now, since we know both of these values on the right-hand side, it's just as simple as plugging it in. So I plug in my 540 kilograms in for the mass of the trailer, and we know that the acceleration is 1.90 meters per second squared. So I do 1.90 meters per second squared. And when we multiply these two together, I get 1,026 newtons. And then finally, okay, watching my sig figs here, I round to the appropriate number of sig figs, and I get that the F, the force from the car in the x direction, which we said was equal to the magnitude of the total force from the car, okay, equal to the total magnitude, the force from the car, is going to be equal to 1,000 newtons. Okay, so that's our final answer for Part A. Now, Part B is pretty simple as well, but I want you to try to figure that one out on your own, but I'll give you a hint before you start on it. You don't need to do any math for Part B. Okay, so go ahead and try Part B on your own, and then continue on to Part C, which I have a tutorial video posted there as well. Okay, if you have any questions, just raise your hand and ask.